So the fundamental concept that you have to know in statistics is the difference between a parameter and a statistic. Parameter is an unknown quantity. All theoretical stuff that we do in terms of deriving, terms of derivations and methodology is always based on parameter. So it's purely theoretical. And why is it theoretical? Because it is not known. Statistic, on the other hand, is an estimated quantity. Estimated, what do we use to estimate? Data. So we use data to estimate the statistic. So statistic is computed using data or a sum. So we do all the derivations using the parameter, and we would end up getting formulas and things like that, and we translate it to a statistic which we can apply in life. Not sure if it should have in chapter 2, but it's better that I talk about it now rather than later. I'm not going to ask you to derive expectations of distributions because this is not problem stats. In probability and statistics course, it goes through expectation, variance, covariance, and moments, and whatnot. So, what is expectation? So expectation of a random variable x, we don't call it a variable in statistics because statistics deals with random stuff. So for a random variable x, the expectation is nothing but from b. So, and that mean is theoretical since it is an unknown quantity and it is a parameter. So when we derive, we actually use the expectation to derive or distribution and expectation moments and so forth. But I give this informal approach so that you can understand how this unknown quantity would relate to the sample mean. Because what would estimate the value of the theoretical mean, you use the sample. Yes. What is a sample mean from 2023? So gonna say the average of all class values, so which would mean how many data points should we have in the n data point. So suppose I have a sample. X1, X2, X3, dot, all the way up to Xn. Each random variable could be some number, right? That could be 10, 10.5, 12, 16, whatever. It comes from a distribution. How do we find the average using those?
Sum them all up and divide by total number of observations.
So you sum them up. And you divide by n, right? Sum of all the observations divided by the sample size is the sample mean. The notation that I used up there, that's x bar is sample mean. Is the sample mean an estimated quantity? Why? I'm gonna say yes, but why?
Sample statistic estimates the population.
So it is a sample statistic, so you estimate it from a sample, it gives an estimate. So it is an estimated quantity. So what is this informal thing that I wanted to mention? Like time series, people. Something over something in detail. So something over something. So anytime you see expectation, an informal way to look at it is simply you're summing the values, dividing it by the sample size. This is for a sample. So how do I go from the theoretical expectation and connect it to a sample? Anytime you see that E, it simply means you're summing I equals 1 to n, dividing it by n. Of course, this is informal. There are cases where you have to do algebra to get it to work properly. But it is a nice way to understand that the expectation is connected to this quantity that I wrote. So what is that quantity? The sample mean. So this and that are one and the same. Agreed? Yes. So if you have a sample, this simply is x bar. Because you're adding all the observations and dividing it by n. So in 3162, who's taking it? What was ready? Juliana and Paul. Anytime they talk about expectation, the corresponding sample estimate, this is how you obtain sum of all the observations, and just replace it by sum and divide by n. So Evan was right, something over something. At least we remember that part. Standard notation for the theoretical mean is mu. The sample mean x bar. Let's see. X bar is an estimate. It's an estimate of the theoretical mean. So if I asked you to give a different notation for x bar based on what I said at the end of class last time and what you said at the beginning of class this time or today, what is another notation for x bar?
X hat.
So close, Joe. There is a hat, but he put the hat on the wrong thing. mu hat because it is an estimate for mu. So you can either call it as x bar or mu hat. I strongly recommend that if you are planning on going to graduate studies, get used to the concept of mu hat. Eventually, it will translate to mu hat. Are we clear so far? Okay. The race. Variance sigma squared. What does variance give us? So sigma squared for variance measures variation in a random sum. Now, gonna mention is how an observation deviates from the mean. Yes. So I'm going to write the formula for variance in a theoretical sense. So x1, x2, all the way up to xn, those are the observations. And they deviate from the mean. So what is the notation to represent that deviation? Say for the ith observation. You go, listen.
x5 minus x hat, and then flip one.
Oh, okay, there you go. One step ahead. The theoretical. I'll put mu here. Like that's the main. Let's say x1's over here, x2's over there, x5 there, 3, 4. How would you want it? The deviation of each observation from the mean. Joe was almost there.
Absolute value of mu minus xi.
Absolute value of mu minus xi. Do we agree with that? Yes. So if this number is 7, that number is 9, and I want to know how far is 9 from 7, simply do x3 minus mu. And since it is a distance, you put, absolute value. But there is a problem with absolute value. In terms of distributions, they are a pain to derive. So we want something easier that we can work with, an alternative to an absolute value.
Square root of that difference squared.
Well, it's just to measure I see what you're saying, just to measure this distance, I could have it as xi minus mu square, and then take the root of it to get the distance. That distance has a name. Math people. So that distance that we have, xi minus mu squared, is the Euclidean distance. In analysis, they call it as the L2 norm. Absolute value of xi minus mu is the absolute value distance. It has a name called Manhattan distance because have you been to Manhattan? So when people ask for, oh, how far is this place from here? Let's say 4 blocks from here. So you kind of go in pieces. It's an absolute distance. So they call that the Manhattan distance analysis, no. But finding distributions for xi minus mu and taking the absolute value is difficult. So we go for that approach. So that's what we have. Good. So that is the theoretical variant. Now, how would you associate it with the sample variant?
Not raise my palm.
The theoretical one is divided by n.
So from here, I want to, oh, sorry.
My bad, I see what you're saying.
Expectation. I give you the answer accidentally. So that's the expectation. The sample one. See, I told you, that's his job. And I don't pay him. So how would we rewrite that? The sample version. I got way too excited. Use the logic that we did earlier over there. And I said I gave you the answer accidentally.
You give the same expectation, but with hat.
How would you rewrite this? Eric. Eric, right? Yeah. Okay. Anytime you see E informally, it would correspond to on that side, I erased it.
Sample mean zero. No. Expected value.
Right, I agree. Over here, I said informally, anytime you see E in your mind, it corresponds to this notation. Evan gave the answer, and I made it correct. What did you say, Evan? Something over something. So what are the two somethings? Sum divided by n. So again, informal, not formal stuff. What should I replace that new by? Because we're talking about a sample.
That next door.
Good. You see how I went from the theoretical variance to sample variance. You have to be a bit careful here. I won't get too much into this, but if you go back to 2023, the formula that we would use for sample variance, same except we divide it by n minus 1, not n. Getting to the theory of unbiasedness and stuff, I won't get into that. Pretty advanced for this class. So this is how the variance is estimated, but we adjust it by a tiny bit over here to get the better estimate of sample variance. That's what you would use in 2023. Good. this is all the basic stuff you need to know for regression. I wanted to get to this part with one important item, which is item. We will be using it a lot in this class. That part is a square. We agree. Yes. Now, that is going to measure the deviation from the mean for each observation. Correct. You're squaring all the values and you're summing them. Yes. So in general, that numerator is called sum of squares. SS. You constantly see that in this class. Some use the notation just S. Forget what the book uses. Has the list. SS is better. But I will check the notation next slide or for next class. So the sum of squares are quite important for our derivations. Are we clear so far? Good. Sum of squares, bearings, mean, theoretical one, sample one. Good. It will do problems. Data.